Today we have Stan Palasek. He's, of course, one of our postdocs here at the Institute and also joined with Princeton University. And he will talk about quantitative regularity for the Navier-Stokes equations in the axisymmetric case.
Thank you, Camilo, and thanks to both of the organizers for inviting me. I'm very happy to be able to give a talk here. So, yeah, as mentioned, I'll be talking about the Navier-Stokes equations today. So, let me just show you what they look like. So we, without the Laplacian, we have the familiar to probably many of us Euler equations, but we add some dissipation, which gives us a lot more hope of proving things in the direction of regularity for these equations. So here I have the initial value problem. So we endow this with some divergence-free data. So for the purpose of this talk, we're mostly interested in classical solutions. So let's say our data is fairly nice. At the very least, it's in L2, but probably we want it to be in some very regular LP space as well. Okay, so U and P are the unknowns. Often we will just project onto the space of divergence-free vector fields, which will eliminate the P. So really, we think of this just as an equation in terms of the velocity field. So let me just give you the most basic properties of the Navier-Stokes equation. So they're for sufficiently strong solutions, we have an energy equality. Of course, it's also common to look at solutions that obey an energy inequality. And if you're looking at weak solutions, those are the Leray-Hoff solutions. But okay, if your solution is of the strong type, you have this exact balance where the amount of energy that's being dissipated by the Laplacian is exactly how much you lose after a certain amount of time. And the other important property
is the square on the epsilon, right?
Oh, so, yeah, of course. Yeah, these are both squared. So of course we also have a scaling invariance. So if for any positive scaling parameter, you can take a solution and arrive at another solution. So if lambda is, let's say, a large positive number, you should imagine that you're sort of zooming in on the solution. So if your solution maybe lives at length scale 1, if you insert a lambda here, you're basically zooming in on the behavior that's living at scale 1 over lambda. So this is like a zooming in operator. And so this motivates how we classify different function spaces in which we might study the Navier-Stokes. So if you perform this zooming in, so you're looking at finer scale behavior, and the norm gets bigger, so this homogeneous exponent is positive, then we say we're in the it's a subcritical norm. If the scaling in procedure exactly preserves the norm, then that's critical, and then A is negative, it's supercritical. So, for example, if you're in 3 dimensions, the energy space, which from this again, there are squares here, is L. You say you're bounded in time and L2 in space, and then the derivative is L2 in space and time. So this scaling corresponds to something supercritical, because if you zoom in, the norm gets smaller, basically. So that's why 3D Navier-Stokes is a supercritical problem, and that's why it's hard to prove regularity. So subcritical means that the norm is sensitive to small scale behavior, and supercritical means it's sensitive to large scale behavior. So this kind of motivates why if you want to control the regularity, you can really only expect this to happen using a subcritical norm. So for example, this is a classical result of Leray, and it is basically a consequence of a fixed point argument. So if you think of this PDE as a fixed point problem, you can solve it with the usual type of fixed point argument. And so you need to assume some smallness of something. So you can make the nonlinearity essentially perturbative if you make the amount of time small, or you can make it perturbative if you make the data small. But in either case, as long as you're in an LP space that corresponds to a subcritical regularity, so in 3 dimensions that's P larger than 3, then you can construct solutions in this way. So the solvability is guaranteed for some amount of time, which is U in the LP norm to some negative power. or if you flip that around, another way of saying that is if the solution blows up, then it must be because the norm is getting big at least at some minimum rate. So this is also classical theorem of Leray. It's an exact pointwise lower bound. If your solution is blowing up, then it has the LP norms for p bigger than 3 have to be growing at least this rate.
Blow up means that I cannot extend it further.
Yeah. I mean, for Navier-Stokes, it's kind of nice because essentially any notion of blow up you come up with is essentially equivalent. But yeah, that's probably the best definition. If you assume your solution cannot be extended while staying in some nice space. Yeah, the nice space part is important because you can blow up and probably continue the solution as a weak solution. But yeah, exactly. The solution will cease being in LP space. So this corresponds to the familiar situation where you're doing a fixed point argument to construct a solution and you're iteratively adding more and more time. But as the norm blows up, the amount of time you can do the fixed point iteration is shrinking and is ultimately summable. And that's what it looks like when you're hitting a blow up here. So you can see that p equals 3 is critical. So this is deteriorating. This is in 2 dimensions. This is actually the energy is exactly critical. So with some extra addition coming from the energy equality, you can actually show that in 2 dimensions the problem is globally well posed. But this criticality issue is essentially why in dimensions 3 and higher the Navier-Stokes problem most likely blows up. Although of course this is still an open problem. So for critical solutions, it's not as obvious. So you can justify the fact that you have local opposedness and regularity for subcritically bounded solutions very easily based on this kind of zooming in idea. But for critical solutions, it's not as obvious. So these heuristics kind of tell you that if your solution is concentrating on smaller and smaller scales, then the subcritical norms have to be getting bigger. It's just the way they're built, because they accentuate small scale behavior, they have to get big. But critical norms are quite a bit different. Like so if you think about this, like L3 norm is critical. It's not as much controlling how small of a scale your solution is concentrating down to. It's more just telling you how many different concentrations your solution has. It doesn't really tell you anything about how much if it's escaping to high frequencies or anything to that effect. It's so non-obvious that Leray, who's kind of the guy who started this whole area and had a lot of the initial brilliant insights, he conjectured that the Navier-Stokes would have a self-similar blow-up. We now know that he's wrong, but it was a very plausible hypothesis that you could have critically bounded solutions that have a singularity. This was not the first time that his conjecture was ruled out, but a notable one for this work is the following. So this big theorem of Escarriaza-Sergin and Schwerak basically says that if your solution blows up, then there must be a sequence of times approaching the blow-up time where the L3 norm is going to infinity. And it's been improved in various ways. So for example, Sergin had a theorem that you can turn this lim soup into just a limit, so you no longer have to take a sequence of times. People have slightly weakened the spaces in which you can do this. Like you can do this in some negative regularity Bessoff spaces, for example. But I mean, this is essentially the sort of strongest qualitative theorem, short of some like technical improvements that one can do. Let me give you a sense of how this works. So I was planning to draw a picture for this. So here's what you expect. So let's imagine that your solution to Navier-Stokes has concentrated down to some small length scale. Let's say that it concentrates down to length scale L. So you can imagine some like very, very small but very high frequency vortex has started to appear. These scaling heuristics suggest that this vortex alone does not necessarily cause the L3 norm to go to infinity. Because what can happen is maybe the width is length L, but maybe the amplitude is more like L inverse. L inverse. So you take the L3 norm and you get something that's basically unit scale. So this alone, this is why the critical problem is hard, because it's consistent with having these very narrow but very tall peaks. So the realization of this is that, well, so in order, this high frequency bubble couldn't have come out of nowhere. There must have been some predecessors to it that also had high frequencies. And you can prove that, roughly speaking, by the same argument you prove local well-posedness. Like if the solution is fairly nice at one point in time, it must be fairly nice for some short amount of time into the future. So there must have been in previous times a bunch of other bubbles that lived at slightly lower frequencies. And the idea is that because of the dissipation term in the Navier-Stokes, right? So remember that the Navier-Stokes is like basically a nonlinear heat equation. Because of this, there must be a little bit of heat that leaks from these high frequency concentrations. So each one of them is gonna at every single scale, it's gonna leak a little bit of its mass outward in space. So if this guy has length scale L, then basically you get a little bit of this leaking at every length scale in between, let's say L and 1. So the number of these concentrations you end up getting, they're basically log 1 over L, roughly speaking. So the other thing you notice is that because of the heat equation, the amount of heat you end up getting at each of these things, you could say sort of because of the heat kernel, is sort of like e to the minus the critical norm squared. So each one of these contributes roughly that amount of mass to the L3 norm. So when you add all these contributions together, you roughly find that the L3 norm must be at least as big as, maybe I'll add the powers just to be precise, that the number of these little bubbles times the amount that each one is contributing. And by the way, I should say this picture, things are a little bit worse in general. So let's say we're in the axisymmetric situation, which is where you can actually justify these things. So when you add up all the contributions, you get this, and that must be smaller than the total L3 norm. And so when you rearrange this, you find that the length has to be at least as big as e to the minus e to the L3 norm to some power. So in other words, because of this heat leaking out, the length scale of this concentration can't be much smaller than something you can explicitly bound from below. And well, because of the way things balance out, if you can't concentrate at a small scale, the solution cannot have too large of an amplitude. So if it has a large amplitude over a large region, of course, that would contradict, let's say, energy conservation, things like that. So you end up getting some theorems like this. So the original one is due to Terry Tao. So he showed that for general solutions, due to this type of argument, the smallest length scale of concentration is bounded by this triple exponential quantity in terms of the critical norm. So this is more the situation I was talking about here. If you assume the solution is axisymmetric, then you can improve this to a double exponential lower bound. And then so if you can put a lower bound on the length scale of the concentration of the solution, you can turn that into a bound on essentially any of the subcritical norms. So this is good enough to bound the L infinity norm of U, or the L infinity norm of the 10th derivative of U, or whatever you like. But so for example, you could get something like this.
Sorry, what is axisymmetric?
Oh, sorry, I should say, yeah, so axisymmetric means that if you consider the solution in cylindrical coordinates, so you think of, you have an R, a Z, and a theta component, then in this coordinate system, the solution does not depend on the axial variable. So if you write the velocity field as let's say a radial component, so of course ER is the component that points in the radial direction, angular coordinate, and a vertical component, then you're saying the components do not depend on the angular variable. So d theta of any of these. So, yeah, some sort of tornado-like solution where. Yeah, people consider the axisymmetric Navier-Stokes because it's sort of it's an intermediate between 2 and 3-dimensional flows. Like it only depends on 2 of the variables, although it points in 3 of the possible directions. And well, there are a number of nice things one can say about it, and it's quite physical because you know, it is a symmetry that is preserved by the flow of the fluid, so it's natural to consider it.
Is it the same thing? It's invariant in the rotation of around the axis, or
Roughly it is, yeah. It's just you have to move the cylindrical coordinates first. Of course, like the Cartesian coordinates are not invariant under the rotation. Like if you know,
If you transform the vector as a vector, it is.
as of yeah.
And if you transform the velocity as a vector, it really is that you're rotating this way, right?
Yeah, I mean, you just have to be careful because it's like you know, if this is the axis and you're pointing this way, and when you rotate it, the vector itself gets rotated as well.
Yeah, but that's the transformation you would put.
Oh, sure.
On the vector physically. Somehow.
Okay.
Right? I mean,
Yeah.
in that sense, it's.
Okay, yeah, I see what you mean.
I guess this result is for solutions with swirl, right? Because
Exactly.
otherwise it's regular. No?
Yeah, exactly. Yeah, I'll get to that. But yeah, if you assume it's axisymmetric and it's not swirling, meaning it's not pointing, there's no component in the theta direction, then it's a well-known result that the solution has to be regular. So of course wouldn't be interesting in that case to talk about regularity criteria. But yeah, I'll get to that in more detail. Yeah. So anyway, these arguments lead you to both a regularity theorem telling you that you can bound the high regularity norms of the solution explicitly in terms of the critical size of the solution. So here I'm using this notation for the iterated exponential. So in the general case, you have 3 iterated exponentials. In the axisymmetric case, you have 2 iterated exponentials, and similar here for the logarithm. So if you combine this type of regularity theorem with the classical regularity theorem that says that the L3 norm has to go to infinity at a polynomial rate, then you conclude that you get some lower bound on the critical norm. Go to infinity, at least along a sequence of points approaching the blow. Actually, it's still open whether one can prove a quantitative blow-up rate that is true for every single point leading to the blow-up time. Would be very interesting if one could do that. Yeah, so what I want to highlight about these results is that the largeness of the critical norm comes from contributions to many different scales. So it says nothing to the effect that any one of these peaks is getting large in the correct dimensional sense. Like each one of these peaks could have the property that its amplitude is like 1 over the length scale at which it lives. It says nothing that any of them should be exceeding that sort of critical size, and that would be interesting because it would be saying that the strength of the singularity has to be getting stronger and stronger as you get closer, not just that it's sort of leaking out heat, making the L3 norm large. So motivated by that, one looks at weaker notions of critical norms. So the weak L3 norm or something that's bounded pointwise is something in this form. So what the idea is, instead of looking at a single peak that's getting narrower and taller, one could imagine something that as time goes on, it's sort of filling out something that's shaped like the graph of 1 over x in terms of its amplitudes, but it's only filling it out at some length scale that's as small as 1 over that's as small as t star minus t to the 1/2. So in other words, as you get closer and closer to the blow-up time, you start approaching this sort of singular profile. At all scales at once, not just a single scale that's getting small. And this can't be ruled out at all by these sort of arguments that I indicated before. Because, well, so for example, even the weak L3 norm, it's basically measuring, can you fit your function underneath a homogeneous function like this? So what is In other words, it says, what is the largest C such that you can fit a rearrangement of your function underneath C over X? So finding a bunch of, little concentrations scattered throughout space that are contributing to the L3 norm doesn't tell you anything about the largeness of the weak L3 norm. They're all happy to fit underneath that 1 over X profile. So type 1 blowups are really not covered at all by those types of arguments. And whether one can rule out type 1 blowups in the general case for the Navier-Stokes is a completely open problem. On the other hand, for axisymmetric solutions, we do have various theorems. So the sort of first notable ones were due to these big teams of authors, so that they're looking at criterion of the form, let's say U is bounded by 1 over R. So, in terms of dimensions, the velocity field is like 1 over length. So U less than 1 over R. So I should just emphasize we're in the axisymmetric setting. So when I say R, I'm referring to the axisymmetric variable. So R would be the distance from the z-axis. So yeah, these teams were able to show that if the velocity is bounded by 1 over R, then the solution is regular. Or this paper, Koch, Nadarashvili, Sergin, Shverak, were able to prove regularity under an assumption like this. But these are fairly qualitative theorems, so they're not giving you any explicit bound. Like this one, for instance, requires one to use a type of argument that's very popular in the area, which is these types of things where you take a singularity and you zoom in, and as you take the zooming scale, smaller and smaller, you take a weak limit and you extract that limiting profile, and then you use some more abstract type of theorem. In this case, they use sort of a Liouville theorem for the Navier-Stokes equations to derive a contradiction. So they show that the zoomed in solution is a bounded solution in Navier-Stokes, a bounded ancient solution, meaning it goes back infinite time. And then they show that there are no bounded ancient solutions except the trivial ones, which rules out any possibility of a singularity satisfying those types of bounds. But if one wants some explicit bounds that actually tell you something about concrete solutions, these aren't very helpful. They don't tell you anything about how fast these norms have to go to infinity, or how large they have to get in order for the solution to have concentrated at a certain frequency level. Why do we care about that? Well, here's some motivation. So authors who are looking for singularities, they do look at the axisymmetric world, partly because it's just easier to understand and there's more structure to take advantage of. So this is a scenario that, according to the author, Tom Ho, is extremely promising. So what you're looking at here is the RZ plane. So in the RZ plane, you have almost a two-dimensional fluid, except of course this is the situation with swirl. So there's an additional velocity component that's pointing out of the board that's sort of mixing together all of these different things. And so you can kind of imagine there's some flow toward the axis, but also around, and there's this chaotic swirl that he's discovered. And okay, he claims that it blows up. Of course, no one has proved it rigorously, so it's still an unsolved question. But the way they evaluate these blowups is by looking at critical norms. So for example, this is from that same paper. He's basically plotting the L3 norm in the vicinity of his blowup, and he's watching it go to infinity, and he's saying, okay, well, maybe that's a good indication that my solution really is a solution.
He's giving a precise initial data problem.
Yeah. He very explicitly writes it.
Then he simulates it.
Exactly. Yeah. And he claims here that he has, I don't remember the exact number,
Yeah,
but
the simulation is a bit more complicated. I mean, he's changing, I think, for instance, the viscosity, he's rescaling the solution, he's doing some stuff.
yeah, I mean,
It's not like taking a simulation with an initial data and then letting it run. I mean, otherwise, I don't think you would see anything.
well, it's for special viscosities, right? If I understand right, he claims that this data works for Euler, and he claims it works for large viscosities. And he claims it does not work for small viscosities. But in this,
Yeah, there's data.
no, it's weird. There's a gap.
There's a gap.
Yeah, this is there's a different paper that he wrote with his student, I think, where I think that's what you're talking about, where there are two different scales. And that one, I think they rule out that there's a finite time blow. It's like you said, they have to change the viscosity as it gets closer.
Okay.
But this one,
This one, it doesn't change the
he
viscosity.
claims it's just a solution to Navier-Stokes, and it happens. He claims it happens at the axis. The numerical simulation, there's a boundary, but the claim blowup is on the axis. So
Yeah, well, that would be, I mean, if the blow up is not at the axis, then of course it would be obviously wrong.
Oh, it would be
for
wrong.
theoretical reasons, right?
yeah. My point is that the numerical boundary is quite far from where the action is happening.
Okay, sure.
But yeah, okay, so nobody knows for sure whether this is right or wrong. But he claims many orders of magnitude of growth of let's say the size of the vorticity, which is
For the size of the vorticity,
yeah.
but not for the L3 norm of the.
The L3 norm looks like this.
Um,
And he had to really refine his computations in order to find any growth at all of this. So this is 10 to the fifth if you can see it. And this is
Right,
10
and
to the fifth.
that's where it gets tricky, right? I mean, he's refining sort of, I mean, there's something going on. It's not like he's taking, say, I don't know, the spectral method on, I mean, there's some refining of the grid.
Yeah, exactly. Yeah, the first time he did it, he didn't see any growth, and then he refined his grid and he found some. Yeah, I don't know. I mean, I'm not qualified to say whether the numerics are right or wrong. But my point is only that as theoretical mathematicians, it pays to understand exactly what a blowup should look like. What types of norms should get large. I mean, I tried to explain, for instance, why I think looking at the L3 norm, the strong L3 norm is a little bit limiting. Why looking at the weak L3 norm might deliver more information about what's happening. So that motivates what we're looking. Yeah.
So I should take it then that the graph that you showed us in the previous slide does not illustrate actually the blow-up. This is that time this is the initial data actually. Because in the next one, he runs it until 1000.
Yeah.
1000. So.
Yeah, the time of blowup happens. I don't remember. It's not that long after this.
No, it is.
So this is 10. Yeah, 2 times 10.
Is that -3?
-3.
Oh shit. Okay.
Yeah.
Yeah,
So
okay,
this is
never
fairly close.
And it's actually very close to 0.002.
Oh, sure. I thought that was 10 to the 3.
Oh, sorry. I should have made it a little bigger.
Okay.
Yeah. I don't know. Again, I'm not qualified to evaluate the numerics, but I just wanted to make the point that these scenarios are things people look at. So it pays to understand what should be happening.
So I know nothing about the field, but I'm a bit confused. So this seems to be a strong suggestion that Navier-Stokes are blowing up. Like he's giving us an example of blow up, even though he cannot prove anything.
That's the claim. Of course, you never know. I mean, it could happen that at scale 10 to the -30, if everything falls apart.
Sure. But like, this is the first paper of this kind, or every second?
Other people have claimed it. This one claims a much larger growth than anyone ever before.
Something that is, I mean,
Since mind blow, like
people have claimed, for instance, that Euler blows up, I don't know, 30 years ago, maybe 35 years ago.
If you watch
And
Tom's
then
talks,
they have refined the computations and.
yeah, Tom's talks will have a list of a chart full of different authors who have claimed blowup, and then what their vorticity growth is, and he makes the point that all these have been wrong before. But he also claims that the growth that he sees is order of magnitude larger than what other people have identified. So.
I mean, to his credit, there was a similar claim. I mean, he has a computer-assisted proof of blow up for Euler and the boundary.
oh, so he's the guy who gave a talk like 1 year ago in Princeton.
That is his PhD student, with whom he actually wrote the paper.
Yeah. I mean, the jury's still out on this, so we'll see. Okay, so this motivates what we're interested in. So we're looking at the weak L3 norm. So the claim is that we can prove in the axisymmetric setting, we can prove a result similar to the one of tau, where we get this this strong bound on the solution, including scattering as c goes to infinity and so forth. But only in terms of the weak norm. So we're not taking into account these concentrations that might appear distantly in space. So yeah, like I said earlier, every subcritical norm could in principle be controlled. I just wrote the L infinity for simplicity. And the sort of a nice thing about this is that unlike many of the estimates you get in this area, it does not deteriorate as time goes on. So often you get some exponential dependence on the time or also on the data in some supercritical norm. So it only depends on this a priori estimate. I shouldn't call it this assumed bound. Okay, so as a sort of primer, I want to do the case of the no swirl, which Dave mentioned. So if you have no swirl, this is very similar to the 2D case, right? So if you think about a 3D fluid and you think about the RZ plane, so the plane that is intersects with the x3 axis, you essentially have a 2D fluid, and actually the further out you go, the larger R is, the more it actually becomes 2D Euler or 2D Navier-Stokes. So in other words, this smaller R term goes away. So just as you might be aware, for 2D fluids, the vorticity gets transported and possibly diffused as well if you have Navier-Stokes. In the axisymmetric no swirl world, there's a vorticity over R quantity which behaves much the same way. So it gets transported and diffused. In addition to being transported by U, it also has this additional term coming from essentially the coordinate singularity at the axis. But nonetheless, this is a very favorable equation. And so if you test this against R and you integrate, good things happen. So when this term goes away for the usual reason, you can integrate by parts and use the incompressibility and it vanishes. This term ends up having a favorable sign when you write it in cylindrical coordinates. That's why this ends up being a less than or equal to, because there's a negative term on the left-hand side that we've, or sorry, I should say a positive term on the left-hand side that we've discarded. And so this is good news because we have a priori bound, assuming the data is regular. So assuming the data has gamma in L2, which follows, for example, by the solution, the data being in H1, for instance, H2 would be good enough. We get an a priori bound on this gamma quantity, and it's a subcritical quantity. It's actually a really, really strong subcritical quantity. It's even better in terms of scaling than just the velocity to L infinity. So that's great news. I should say I'm doing some formal calculations. So in order to really justify things, you're going to want to introduce some cutoff functions and things like that to be precise. But everything works out if you're sufficiently careful.
You could even use the maximum principle, I guess, in this case, right?
Yeah, I suppose you.
Isn't that what Yudovich and?
Yeah, you have to be careful in it because, of course, the coefficient has a singularity.
And it has a favorable sign, no?
Probably. I mean,
isn't that what Yudovich actually does in his original paper? Because this is Yudovich's original paper, I think.
I didn't actually look at his original paper. I think
Yeah, maybe he runs some energy estimates.
Yeah, I'm not sure. I know Lady Shenskaya, and she has one I think with the co-author, and they do this, and they do it more this way.
They do it in the energy estimate.
Yeah, but I haven't looked at all the original sources. But yeah, I mean, okay, so this is a great equation, so I'm sure there are many ways one could go about proving regularity. Anyway, I won't bore you with all these details, but basically, normally you'd have no chance of closing this sort of energy estimate. But in this case, you can do some Holder. You can do some Holder inequality on this, and gamma comes out beautifully because it's omega theta over R, and okay, Young's inequality, and you can close this energy estimate. Apply Gronwall, and you get something that's great. And then you'll see why I'm excited about the theorem that I claim not involving time or the data, because you see when you do these things in the most straightforward way, you end up getting an estimate that really, really deteriorates as time goes to infinity or depending on the data. So how do we approach the with swirl situation? So it's very much extension of the no swirl case. So the beautiful idea of Chen, Feng, and Zhang is to so basically the omega theta over R quantity, it only controls the velocity field in the RZ direction. You can kind of imagine the right-hand rule. If the vorticity is in the theta direction, then it corresponds to changes in the RZ plane. So introducing this phi, which involves the R component of the vorticity, this deals with the theta component. So it sort of compensates for the other one. So this ends up being, I think, omega R is negative dz of u theta. So now we have a complete picture, and this is the system you get. So when you just write this down, it looks kind of unremarkable. It's not clear why this is an improvement over working with just the vorticity or anything else. You'll notice, first of all, that, I mean, this is obviously just a more general version of what we had here, right? Here we had 0 on the right-hand side, and now we have something more complicated because the swirl was not assumed to be 0. But the remarkable thing is that you can nearly close these energy estimates at the critical regularity. So if you, I'll just do the gamma one just to illustrate. So if you multiply this by a gamma and integrate, so you get something like this. So you do the same trick where you get the negative term, and this ends up being the right-hand side. And then, okay, there are different ways one could try to see from this that you're getting something favorable. But one way would be, okay, so you have omega r over r. That's what we defined to be phi. And all that's left is u theta over r. You could distribute this r between the two factors, put everything in L3. Recall that L3 is a critical norm for u. So that's why I'm saying this almost closes at critical regularity. So let's assume that our, maybe have some good L3 estimate on u theta. There's a Hardy inequality that lets you convert these negative powers of r into derivatives. So you have some, so you can estimate this by the gradients in L2. And well, now you have a sense of how you could close this energy inequality, because if you have a similar bound for the phi variable, you could put them together and you could get something that closes. And so it's like you're almost there. Just for comparison, for the full 3D Navier-Stokes, there's nothing even remotely similar to this. You have no chance of closing any sort of energy estimate because the problem is so supercritical. So that's what I said. I just wanted to make a side remark. Whether you can prove a regularity theorem in terms of only the L3 norm of u theta is a totally open, very interesting question. It's known that if the L3 norm is small in the vicinity of the axis, then you have regularity, but not in general. So that would be nice to know.
Wait a second. So is that a typo? L3?
Oh, sorry.
Okay, right. I mean, because the L2 estimate you have that.
Yeah.
Okay.
Sorry, it means to be L3. Yeah. Okay. So let me remark in terms of how we approach this from in our theorem. We use a different, very special quantity.
So sorry, if you go back, why you're saying so? It's an open problem if u theta in F3 stays bounded, but on the other hand, in your inequality, only u theta appears. What is the catch?
Yeah. I mean, but you can't close this because it's large. It could be large.
You cannot close it because it's large.
Yeah. So if you that's what Chen Feng and Zhang do. They show if it's small.
You need it to be small enough, and then
Yeah.
You can do it. Okay.
Yeah. So yeah, my co-author and I work pretty hard trying to do this, and it's not at all clear how to do it. Okay, so we use a different property, which is also well known for the Axisymmetric Navier-Stokes, which is this quantity called the swirl. So you take the angular component of the velocity and you scale it by r. It looks weird, but it actually has a remarkable PDE that it satisfies. So you see that the right-hand side is 0, right? So that's incredible news. And in fact, this implies something that a lot of people use in this line of work, which is the fact that this obeys a maximum principle.
Yeah, so but that's the same that you could have used when I told you.
Right.
You could have used the maximum principle in the other case as well, rather than multiply by. I mean, in the no-squid situation.
Yeah.
It's exactly the same.
But the difference, I thought, the difference here is that this vanishes on the axis, which definitely helps you. I'm not sure the other one.
There's a formal problem, you mean?
Yeah, I think that's how you get around the issue that the drift has a singular term.
Yeah, but that's I think why, for instance, in Tarek's work, you have to assume it's a little bit more regular.
Yeah.
Then actually that omega theta divided by r is actually not bothering you so much.
Sure.
If you okay, I mean, if you I think if you assume much more regularity of the initial data, you can actually work with that quantity.
Okay.
And I think that's actually what Judovich and collaborator do in that paper.
Okay, that makes perfect sense then.
Right. I mean, that's why Tarek's paper, he proves the Blowup if it's a lower regularity, like, C alpha or whatever.
Right.
But if you assume it's, I don't know, C1 alpha,
Right.
that quantity is actually a good one.
Right. If the vortices is.
Yeah, I mean, it becomes better. Yes.
Right. Okay, that makes sense. Okay. Yeah. And anyway, the key thing here, of course, is that the swirl vanishes at the axis, right? So somehow you can do your maximum principal argument away from, on a neighborhood away from the actors. So anyway, yeah, we don't really need to directly use this in ours. Rather, we use a different property. Okay, most of the credit for this proposition goes to Nazaroff and Uraltseva. We really just made it quantitative. So here's what it basically says: if you have something that obeys this great PDE, then what you get is a Harnack inequality for it. And one of the consequences of the Harnack inequality is that if the drift satisfies this sort of critical, and actually, sorry, I made a typo. This needs to be rescaled to make this a scale invariant quantity. So it should be divided by the length, the volume of Q prime raised to the power that makes this a dimensionless thing. Sorry about that. But if the drift obeys this sort of critical bound, then the solution to this drift diffusion equation is Holder. And moreover, the Holder exponent that you get depends on the norm of the drift. So it's an exponential. So this is where one of the two exponentials in the theory comes from, is this unfortunate exponential dependence. But yeah, so the main highlight is that we can make this quantitative, and what this amounts to is a slightly subcritical estimate. So this drift can be controlled in terms of our weak L3 norm. That is not terribly difficult to show. And so the swirl is Holder, and also the swirl vanishes on the X3 axis. And so therefore, if you apply Holder to something that vanishes, right, it must be big O of R to the gamma in the vicinity of it. And that leads to this slightly subcritical estimate. The reason I say slightly and emphasize that is because this gamma is so small in the sense that it depends exponentially on the critical norm. But still, this is enough that we can leverage it and close some energy estimates. For demonstration purpose, if you return to our energy estimate for gamma, for small r, so the fact that this gamma is so small, in order for this to be useful, we need to make we sort of break up the domain into an area that's very close to the axis, and then the part that's further away, you have to look very close to the axis in order for this to actually be useful. So it ends up being exponentially close, like e to the minus gamma, where again gamma is itself exponentially small. But nonetheless, if you consider this very small region, then that allows you to get a small enough coefficient in front of this term in the energy estimate. In fact, I write this out here. For larger R, well, the PDE is essentially two-dimensional, as I mentioned. So these 1 over R's become relatively harmless, right? They turn into, you can bound them by 1 over this threshold you set between the small and the large R's. So you run into the same difficulty we did in the toy problem of the swirl-free situation, where the energy estimate gives you this exponential growth in time, and moreover, the rate at which the exponential is growing is related to this very small R naught that we chose. So this is very harmful if we lived in there. The insight that lets us get rid of this is that instead of running these energy estimates starting from the initial data at time 0, let's say we want to bound on our solution at time t, we can instead pick a time that's very close to the desired t, and run this energy estimate on that small interval. The issue is, okay, this t I pick to start my energy estimate, they don't necessarily have that the gamma is bounded in L2 at that time, right? I mean, the gamma again is a very, gamma being in L2 is a lot to ask, and it's not just generically true. That's more what we're trying to prove, is that gamma is bounded in L2. But what we can do is we can use the partial regularity of the Navier-Stokes in time. So this is a property of the Navier-Stokes that's been used in this other quantitative work, which is the fact that for 3D Navier-Stokes, the solution is smooth for all time except a set that has 1/2 dimensional Hausdorff measure, right? So as a result, close to any time, we can find a time that is where the solution is regular. And so in particular, if the solution is regular at that time, we can find locally, basically, we can make the gamma be bounded in L2, and from that time we can run the energy estimate. So that's essentially how this works, and thus at every single time we can get good estimates on gamma and phi.
So you need to quantify this, I guess, right?
Yeah,
I mean, it's like a bit in the Lelay's argument. I mean, not only you have a lot of good times, but you also know how big it's.
Yeah, exactly. So the way it works out is that if I give you it helps actually a lot having the critical bound. It's important. Because if you try to, so in Lelay's work, he's just using the energy bound. But if you use the energy bound, then all the scaling gets messed up. Because for example, the bounds you end up getting in the regular times will end up depending on the energy. But the energy being supercritical, it's not gonna be as strong as it.
So you're running it on a different quantity.
Yeah, exactly. We're basing it on because it turns out if you take these critical bounds, like a weak L3 bound, for example, you can do an energy estimate for Navier-Stokes where ultimately all the right-hand side only involves the critical norm. You actually have to break the solution into multiple pieces. You have to break it into one piece where you're doing energy estimate and one piece where you have a Picard iteration. So you have the splitting of like a smooth part and then a part that has finite energy yeah, that ends up working out. Yeah, so there are a lot of technicalities. I'm sweeping under the rug, of course, but when you combine those two elements, you can get this partial regularity in time. And it turns out that if I give you a time interval of length t, let's say, I can find a subinterval of length t divided by the critical norm to a power, where the solution is bounded by t to the appropriate negative power, depending on the dimensionality, times the critical norm to some constant power. So yeah, that is essentially what it delivers.
Okay, so it's quantitative and sample, actually.
Yeah, it's very quantitative and critical.
So this theorem is for Leray-Hoff solutions then?
You could probably extend it to Leray-Hoff solutions that have the appropriate critical bound. We didn't do that. We worked in the category of smooth solutions just to avoid technicalities, but it seems very likely that one could, if you were willing to insert, the appropriate cutoffs and modifiers and things, you could probably extend it to a rougher class. Yeah. But yeah, that would just be a lot of work that no one's done. But yeah, probably true. Okay, and yeah, so this is roughly how the argument works. I didn't want to. I think we put this picture in the paper, but I think it really adds more confusion than is necessary.
But it's a good occasion to explain it to us. Like, seeing the picture and I wasn't sure.
Yeah. I mean,
explain it in words. What happens?
Yeah, sure. I mean, so you have to, you get these bounds on shorter and shorter intervals. So ultimately, you want to bound at time 1. So you sorry, I should say that the part of the argument I've really gone through and explained is so t. Yeah, now I'm not even sure what it was. Yeah, I don't actually know. I think I did. I could explain to you later. But anyway, okay.
Because it seems you're actually even going higher with the derivatives, right? I mean, like,
yeah, okay.
There you were like picking up a second derivative and then.
Yeah, so part of this is really once you've gotten so the main part I explained was just how do you get the bound on the gammas in L2. And then once you have this, so that's what this line dictates is on this interval, we have this
okay.
bound.
Then you're doing a bootstrap.
Exactly. Yeah.
Okay.
Yeah. So okay. What ends up happening is the gamma is actually it corresponds to roughly the curl of the r and z components of the velocity. And so if you have a bound on gamma, then you can bound the r and z components basically in L6. So that kind of is what enters in here, and then yeah, you basically use the semi-group for Navier-Stokes to just bootstrap these.
But why can't you simply use Brody, Sedlin, just say like, okay, yeah.
One tricky thing though, so this is another technicality I swept under the rug was you have to work in these local L3 spaces, which are very annoying.
So you can't use the
Yeah,
classical.
everything is very local, which
So you can't use the classical theorem.
yeah. So there are all of these very like local estimates for these pseudo differential operators we have to deal with. It's somewhat annoying because the thing I mentioned, the local regularity in time, or I should say partial regularity in time, it gives you a bound on, let's say, the second derivative of the velocity in L2, for example. But the gamma, sorry, not L2, a higher order than L2, but we want the gamma to be in L2. So that requires some decay in the X3 direction. But that decay is not actually given to us in terms of any a priori bound that we have. And we don't want to use the energy because it's the supercritical thing, so it's going to mess everything up.
And if you cheated and, for instance, took it, I don't know, periodic on the third direction,
Yeah, that would solve the
would it
problem.
become much easier?
It would.
Okay, then you could use the usual stuff.
Yeah, that would definitely simplify things. Yeah.
Yeah, okay, which sounds, of course, a little bit a weird domain because it's periodic in the Z axis.
Yeah.
But
Yeah, I don't see any reason not to do that. But yeah, you could. It would just sound fun. Yeah. Anyway, okay. I guess I'll leave it there and ask for questions.
okay, thank you. Questions? Well, you got many during the talk, so.
Yeah. What?
Okay, thank you.
Yeah, thank you.